Good morning, students. Today we are going to start chapter number 4, Atomic Structure and Chemical Bonding. The idea of the smallest unit of matter was first given by Maharshi Kanad in the 6th century BC in India. According to him, matter consisted of indestructible minute particles, very small particles that cannot be destroyed, called Parmanu, which comprises of two words, Param and Anu, meaning ultimate particles. Now this word Parmanu is known as atoms. A Parmanu does not exist in free state. Rather, it combines with other Parmanus to form a bigger particle called Anu, which is now known as molecule. The Greek philosopher Democritus called the Parmanu as atom, which comes from the Greek word atomos, meaning indivisible. In 1808, John Dalton gave the first scientific theory about the structure of matter. He considered atoms as indivisible particles that are the fundamental building blocks of matter. The existence of different types of matter is considered to be due to different types of atoms constituting them. The main postulates of the Dalton's atomic theory are as follows. Matter consists of very small and indivisible particles called atoms. Atoms can neither be created nor destroyed. Atoms of an element are alike in all respects, but they differ from the atoms of other elements. Atoms of an element combine in small numbers to form the molecule. Atoms of an element combine with atom of another element in a simple ratio to form the molecules of a compound. And last, atoms are the smallest unit of matter that take part in a chemical reaction. The latest research on the atoms has proved that most of the postulates of Dalton's atomic theory are incorrect, except that atoms take part in the chemical reaction. One of the first indications that atoms consist of subatomic particles, that is, they are made up of charged particles, has been put forward by the studies of static electricity and the conditions under which electricity is conducted by different substances. Definitions for atom. Atom is the smallest particle of an element that exhibits all the properties of that element. It may or may not exist independently, but takes part in every chemical reaction. Element. An element is a pure substance that can neither be decomposed into nor formed from simple substances by the ordinary physical or chemical methods. William Crook, a British scientist, noted that gases are ordinarily poor conductors of electricity. However, when a high voltage 10,000 volts charge from an induction coil is applied to tubes filled with gases at a very low pressure 0.01 mmHg, the gases become good conductors of electricity and begin to flow from cathode to anode in the form of rays. Since these rays originate from the negative plate, that is the cathode, and travel from the cathode towards the anode, so they are called cathode rays. Later, J.J. Thomson studied the characteristics and the constituents of cathode rays. The apparatus used by him is called the discharge tube or a cathode ray tube. A discharge tube is a hard glass tube fitted with two metal plates known as electrodes, one of which is connected to the positive terminal of the battery and is called the anode, while the other electrode is connected to the negative terminal of the battery and is called the cathode. It has a side tube through which the gas can be pumped out by using a vacuum pump to create vacuum. When electrical discharge of 10,000 volts is passed through the gases at very low pressure 0.01 mm, cathode rays are produced. Properties of cathode rays. They travel from the cathode to the anode in the straight lines. They cause a greenish yellow fluorescence on a soda glass screen placed in the tube. They produce the shadow of an opaque object placed in the path. They penetrate through the matter. When a beam of cathode ray is made to fall upon hard metallic targets like tungsten, X-rays are produced. They are affected by the electric field, that is, they are inflected towards the positive field and deflected away from the negative field. This shows that they carry the negative charge. They cause ionization of the gas through which they pass. The ratio of the charge to mass of the particles constituting cathode rays remains same, irrespective of the nature of the gas taken and of the metal forming the cathode. They make a light paddle wheel rotate which is kept in the path of the cathode rays. From the experiments, Thomson concluded that cathode rays consist of negatively charged particles, now called electrons. The name electron, meaning atom of negative electricity, was given by Johnson Stoney. These negative particles are an integral part of all atoms. Electrons have both definite mass and definite electrical charge, both of which are independent of the nature of the gas in the discharge tube. Properties of electrons. Electrons from all the sources are alike, having identical mass. They are a constituent part of all atoms. The mass of an electron is 1/1837 times the mass of a hydrogen atom, or 9.108 into 10 to the power minus 31 kg. An electron carries unit negative charge of magnitude minus 1.602 into 10 to the power minus 19 coulombs. The electron is extremely small in size and its radius is less than 1 into 10 to the power minus 15 meters. So, electron can be defined as a subatomic particle having a unit negative charge and a mass equal to 1/1837 of hydrogen atom. It is denoted by the symbol E0-1. The superscript 0 represents its mass and subscript -1 represents its electrical charge. Atoms are found to be electrically neutral. So they must contain, in addition, particles that are positively charged such that the total negative charge of the electrons is equal to the total positive charge. The realization led to the discovery of the positively charged subatomic particles called protons. Discovery of protons. Goldstein performed an experiment by using the discharge tube containing a perforated cathode with small holes. The cathode with small holes is called the perforated cathode, so as to allow the anode rays to pass through it. When a high voltage, about 10,000 volts of electric current was passed through this cathode, and air inside the discharge tube kept at a very low pressure, about 0.001 mm of mercury, a faint red glow was observed behind the perforated cathode. This showed that some rays were produced from the anode and moved from the anode to the cathode, causing the glow behind the cathode. He named these rays as anode rays containing particles now called protons. Properties of anode rays. Anode rays travel in a straight line. They consist of minute material particles and hence produce mechanical effects. They are made up of positively charged particles. Positive rays are deflected by the electric and magnetic fields, but in a direction opposite to that of the cathode rays. This means that these rays consist of positively charged particles called protons. These rays produce fluorescence on a zinc sulfide screen. Their E to M, that is charge to mass ratio, differs from gas to gas. Its value is much less than that of an electron and is maximum when hydrogen is taken in the discharge tube. Properties of protons. A proton possesses a unit positive charge +1 of the value 1.602 into 10 to the power minus 19 coulombs. Its mass is the same as that of hydrogen atom, 1 AMU, that is 1837 times the mass of an electron, which is 1.672 into 10 to the power minus 24 grams. The proton resides in the central part of an atom, that is in the nucleus. Proton may be defined as a subatomic particle having mass 1 AMU, that is equal to hydrogen atom, and has unit positive charge. It is denoted by P1 plus 1. The superscript 1 represents its mass 1 and the subscript plus 1 represents 1 unit positive charge. Proton is formed by the loss of an electron from a hydrogen atom. Hydrogen minus electron gives H plus proton. After the discovery of electrons and protons, J.J. Thomson proposed plum pudding model of the atom. According to this model, an atom is considered to be a sphere of uniform positive charges, and electrons are embedded into it. The total positive charge is equal to the total negative charge, so that an atom as a whole is electrically neutral. The mass of an atom is considered to be uniformly distributed. In 1911, Lord Rutherford, a scientist from New Zealand, directed a stream of alpha particles towards a very thin 1/millionth of a centimeter gold foil. He selected a gold foil because he wanted as thin a layer as possible, and gold is the most malleable metal. He observed that most of the alpha particles passed straight through the foil. Some alpha particles were slightly deflected from their straight path, and very few, nearly 1 in 10,000 alpha particles, were either deflected back by large angles or completely bounced back. Later, Rutherford generalized these results of alpha particle scattering experiment and suggested a model of the atom that is known as Rutherford's atomic model. According to the Rutherford atomic model, the atom contains a large empty space, extra nuclear space. This is why most of the alpha particles pass through the metal foil without deviating from their path. There is a positively charged mass at the center of the atom, known as the nucleus, in which the entire mass of the atom is concentrated. Therefore, the nucleus is the densest part of the atom. The size of the nucleus is very small as compared to the size of the atom. This is proved by the fact that most of the alpha particles pass straight through the gold foil. The electrons revolve around the nucleus at large distances from each other and from the nucleus in circular orbits found in the empty space of an atom. An atom is electrically neutral because the total positive charge of the nucleus is balanced by the total negative charge of the electrons. Electrons revolve around the nucleus in closed circular paths or orbits. The force of attraction between the negatively charged electrons and positively charged nucleus is counterbalanced by the centrifugal force acquired by the revolving electrons. Rutherford's model of atomic structure is similar to the structure of the solar system. Just as in the solar system, the sun is at the center and the planets revolve around it. Similarly, in the atom, the nucleus contains the main mass and the electrons revolve around it in orbits or shells. Drawback of the Rutherford's atomic model. The comparison of electrons with planets in the solar system is the main drawback of Rutherford's atomic model. According to the classical law of mechanics and electrodynamics, if an electrically charged particle is in motion, it inevitably radiates energy. Thus, an electron, when moving around the nucleus, continually should radiate energy, that is, lose energy. As a result, it should gradually pull towards the nucleus and end up colliding with it. This should result in the total collapse of the atom. If it was so, the atom should be highly unstable, and hence matter would not exist in the form that we know. However, we know that an atom is structurally stable. Thus, Rutherford's model failed to explain the stability of an atom. In 1913, a Danish physicist, Niels Bohr, proposed improvements in the Rutherford's atomic model and was able to explain the stability of an atom. According to Niels Bohr, the electrons revolve around the nucleus in fixed circular paths called orbits or shells. Each orbit or shell is associated with a fixed amount of energy, and that is why they are also called the energy level. While electron is revolving around the nucleus in an orbit, an electron neither loses nor gains energy. An electron revolving in a particular orbit, on gaining a certain amount of energy, jumps to the next orbit and vice versa. Since each orbit is associated with fixed amount of energy, so it is called the energy level. For convenience, these energy levels are labeled as K, L, M, N or 1, 2, 3, 4, etc. The orbit closest to the nucleus is the K shell. It has the least amount of energy and the electrons present in it are called K electrons, and so on with the successive shells and their electrons. Discovery of neutrons. By now, it was known that atom contains electrons and protons, and the atomic mass of electron is negligible. Therefore, an atom of helium which contains 2 protons should have a mass of 2 AMU. But the atomic mass of a helium atom was found to be approximately 4 AMU, atomic mass unit. It was therefore proposed that in the nucleus of an atom there must be another particle. This particle should not possess any electrical charge and must be equal in mass to the proton. So, in 1932, Chadwick discovered these particles by bombarding light nuclei like beryllium with the alpha particles, that is helium nuclei, and he got the carbon atom with neutron. These particles are found to be neutral, so they are named neutrons. So a neutron is a subatomic particle or fundamental particle of an atom with no charge and mass almost equal to the mass of the proton, that is hydrogen atom. Neutron is denoted by symbol N10. The superscript 1 represents its mass and subscript 0 represents its electrical charge. Properties of neutrons. The particle was not found to be deflected by any magnetic or electrical field, proving that it is electrically neutral. Its mass is equal to 1.676 into 10 to the power minus 24 grams. That is 1 AMU, atomic mass unit. After the discovery of electrons, protons and neutrons, the subatomic particles, it was found that all atoms have the following similar basic structure. Electrons are negative charged particles that are found outside the nucleus. Protons are positively charged particles that are found in the nucleus of an atom. Neutrons are electrically neutral particles that are also found in the nucleus. Neutrons are slightly heavier than protons. Comparison between Dalton's atomic theory and modern atomic theory. According to the Dalton's atomic theory, atoms are indivisible particles. According to the modern atomic theory, atoms are divisible into subatomic particles, protons, electrons, and neutrons. Atoms, according to Dalton's atomic theory, cannot be created or destroyed. According to the modern atomic theory, atoms can be created and destroyed by nuclear fusion and fission. According to the Dalton's atomic theory, the atoms of an element are alike in all respects, but they differ from the atoms of other elements. According to the modern atomic theory, the atoms of an element may not be alike in all respects, as is seen in the case of isotopes. According to Dalton's atomic theory, atoms of elements combine in small whole numbers to form molecules. According to the modern atomic theory, in the formation of organic compounds, the numbers can be very big, such as thousands.